Okay, so I'm going to get started. Today we're going to look at number properties and divisibilities. And we're going to go through two questions. One question will be fairly easy. One question will be quite difficult. I'm actually going to ask you to tell me your thoughts about how you'd approach the question. You might even get the answer, but I want you to tell me how you'd approach it. So this is going to be a little bit different because I want to see your first impressions, and then we'll talk about all the ways you'd solve it, because you want to solve it quickly, okay, in a math competition. And you want to have multiple ways of solving them. So our agenda today, we're going to look at common phrases, we're going to look at related theorems, and we're going to look at practice problems. Like we said, common phrases, rounding, right? What's the nearest, what's the closest, and to the nearest. You think to yourself, oh, I've got it figured out, and then you realize, oh, you might get the question wrong just because you didn't pay enough attention to the rounding. The nearest, the closest, or to the nearest. Especially when it comes to writing your answer on a math competition. If they say, give it to the nearest month, and you write 30 days, it's wrong, right? That's also common in time. It's also common with currency. And sometimes they'll try to trick you, right? When you pay with currency, how many decimals do we have when you pay with currency? That's correct, right? And so what if it says round to the nearest thousandth? But it's a currency, right? Your default, what your brain will say is, I'm going to round to 2, right? I'm going to say 1.35 or $1.25. But the question will say round to the, and it will give you something, and you have to pay attention to that, right? So just pay attention to it when you're doing this. So I'm going to give you this example. I'll read it to you, and then I'm going to ask you to tell me what you think. So Jerry and Sylvia wanted to go from the southwest corner of a square field to the northeast corner. Jerry walked due east and then due north to reach the goal. But Sylvia headed northeast and reached the goal walking in a straight line. Which of the following is closest to how much shorter Sylvia's trip was compared to Jerry's trip? So what are your thoughts on this question? Should have a few thoughts right away.
Well, wait, so more like the answers were just like how
you'd solve it. What's it about? What are the equations you're going to use? What's the first thing you're going to do?
Like find because I know that like the triangle, like the right angle.
Yeah. Pythagoras' theorem,
yeah.
Right? Always. So you realize right away, okay, this is Pythagoras' theorem. But you don't have a calculator, right? So you know you're going to use Pythagoras' theorem. That's good. Did you have any other thoughts, any different thoughts about this question?
I would draw a diagram.
Draw a diagram. Perfect. Always draw a diagram. Hint is whenever it's a directional question, you're almost always using Pythagoras' theorem. No problem. Simple. So you draw your diagram. So your diagram is going to be simply like, okay, she goes, sorry, that one doesn't work. So she goes, they wanted to go from the southwest corner of a square field, so we know it's a square field, right? That's another key thing. Let's find a marker that works. That works enough. So a square field will have equal sides. So let's try the whole field. And then Jerry walked due east and then due north. So here's Jerry. He walks due east, and then he walks due north. Sylvia decides to go right across. Okay, no problem. Now I'm going to test your math competition skill thinking, right? So what do we know about Sylvia's route versus Jerry's? Go ahead.
It's shorter.
It is shorter, but the question says how much shorter? So let's put it into algebra. What is Jerry's route when it comes to algebra? Yeah.
The HBC, right? For like the Pythagoras.
Yeah, a squared plus b squared equals c squared. Right. So Jerry's root, let's just call it x, right? So x and x. So what's Jerry's root? Close. It's the distance, so it's x plus x. 2x. Right, good. So Jerry's root is 2x. Okay. What's Sylvia's root? So we know our theorem is a squared plus b squared equals c squared, right? So the a and the b are the same, which is x, plus x squared equals c squared. So that would be 2x squared. And then to find c, we have to take the square root of that. Right. So, but now, let me ask you one question. What is c? What is the square root of 2x squared? 2x is actually not correct. So it is the square root of 2x. Right? Because when it's squared, the 2 is squared as well, so it becomes 4. So, right. So just to be aware of it. So now we have to look at this question now, and let's put in numbers. So I know you don't have a paper in front of you, but let's look at this question in terms of, okay, you're doing a math competition now. Okay, let's plug in the numbers. So let's select numbers, one for Jerry and one for Sylvia. So we have a square field. Perfect. Okay, Sylvia walks across. This is our C, but we'll just call it Sylvia's. This is Jerry's root, which is x and x. Okay, so let's pick some numbers to put in our formula. A squared plus b squared equals c squared. Pick some numbers for Jerry's root. I'll get you to pick some numbers. 2. Great number. Okay, so 2 plus 2 squared equals c squared. Okay, great. So then we walk through that, and we get 4 plus 4 equals c squared. Then we get 8 equals c squared. And then we're stuck at this part. And this part is, okay, the square root of 8 equals c. What's the square root of 8? Right, you don't have a calculator. Right. So how do we solve this question without a calculator? Go ahead.
Because it's 2, so instead of 2
And another question, I'll interrupt, is do we need to know the exact answer? No. What do we need to know?
How much longer?
How much shorter the trip is, right? That's the key word, because if you told me longer, the longer's here, right? So these questions you have to be very, very specific. So the longer's here. So I'm going to go to you now. Do we need to know the exact number? No, we don't. And what is the range that we can guess in? It's quite close, right? Well, I mean, we can kind of guess, like if we figure out one trip's like 10 and the other trip's 7, we know that the one is 30% shorter. It doesn't matter if it's 7.2 or 7.4 or if it's 6.8. Like we have a wide range to guess from, right? So knowing that, we can say, okay, I don't have a calculator. I have a wide range of guessing, right, for which to do it. So what, and I have to square my number, right? So what's a number that's easy to square?
4?
Take the square root of, sorry. What's the number that's easy to take the square root of? 100, 49, 16, right? All of these are pretty easy to take the square root of. So we need to square numbers, add them together, and then take the square root of those, okay? So as in math competitions, you know from in your back pocket all the squares, all the square roots, you even know the cubes, right? Because you got to do it fast. So doing this, you say to yourself, okay, what are 2 numbers that I could square and add together? That would be a number I could easily guess the square root of. Okay, and I'm going to list some numbers to you. 16, okay? 49, okay? 100. 16. Okay, so if we did 16 plus 16, like if each side was 4, and we did 16 plus 16, we'd end up with 32. What's your estimate of the square root of 32? Tough, right?
Yeah, tough.
Okay, so what if we did 49? if we did 7 on each side, let's try 7 on each side. We go, okay, my head goes, okay, if we do 7 on each side, right? What's 7 times 7?
49.
Yeah, so the square, so it's 7 squared plus 7 squared equals c squared, which is 49. No, not 49, the addition of it. So that's 98, right? That's about 100, right? When we guess our square root of 100, we get the difference between 10 and 7, right? So how much shorter is the trip?
30%.
Exactly, right? So all of this stuff is different than your traditional mathematics because you can't use a calculator. And they don't want you to find the actual answer. What they want you to do is keep your mind around every single word, because they're trying to make you confused, and see if you have the skills to answer the question without any calculator. Did that make sense?
Think so.
Think so? Part of it did for sure. Sorry to put you on the spot, but we only have 2 students. So, great. So that's the idea of it. So with these kind of questions, these are all the kind of things you're trying to pull out. And when we teach you, we're showing you all these tricks. Because the difference between getting 100% and getting 94% or 93% is your speed. Because these questions, to be able to do that stuff fast, means you have more time for part C. And part C, you need the time. And also to double check. Because there's different ways that you can double check these questions. And we'll see that with the next one for sure. So moving on to the next question. Yes, let's go back. I will take a...
Is it possible to double check how because I finished the last question on the last minute.
Yeah.
Is it possible to double check over
Over that kind of question, no. But what you want to do is, well, there is possible questions. I'll show you with the next question, actually. Because the next question takes 12 minutes, I would say, to solve accurately. But you can double check it in 20 seconds. So when I first looked at this question, I solved it in 20 seconds. And then the long method was the double checking. So yes, there are some of those part C's that you can double check instantly, right? This one, what I would do with this one, personally, is I would look at it, and I would do that quick 49, I'd solve it, and then I'd do the harder math to double check it, right? So you would always have 2 methods, so it is definitely possible. But the thing is you're not entirely completely sure with your quick solutions, okay? So we're going to go into the next one. And yes, so you would use the Pythagoras theorem and the fact that the side lengths of a square are equal. You guys did that one very successfully. Then you let each side length be x. J walked along 2 sides, which is 2 of the side lengths, so he walked 2x. S walked diagonally, so her distance is found through the Pythagorean theorem. Great. Another thing, a common phrase is greatest possible, least possible, biggest, smallest, largest, mean, right? If they said mean, if they said average, these things trip students up, and we see it all the time. Okay, so let's take this example. Much harder. I want you guys to take a minute. I'll read it to you, but then you'll have to read it again yourselves, and we'll see how it goes. All of the numbers 2, 3, 4, 5, 6, and 7 are assigned to the 6 faces of a cube. 1 number to each face. For each of the 8 vertices of the cube, a product of 3 numbers is computed, where the 3 numbers are the numbers assigned to the faces that include that vertex. What is the greatest possible value of the sum of these 8 products? Now this is right from the grade 10 test. So take another minute, read it again, see if any of it makes sense. I'll try to draw some cubes on the board. So at this point, you should have understood the question. But I want you to ask questions to me. Do you have any questions about this? Does it make sense to you? Not at all, eh? Kind of? A little bit? A little bit. Okay, so let's first, you did the right thing the first time, and you said, I would draw it out. So we draw it out, we draw a cube, right? So we have to remember, okay, so there are 6 faces. So here are your 6 faces. 1, 2, 3, 4, 5, 5, 6. Top, bottom, and the other 4. Then there are 8 vertices, okay? So we look at these. Okay, so there's 8 of these. Okay, so now that we've got this compartmentalized, we know we've got 6 faces, we've got 8 vertices. Let's break the question down more. And if this was my actual teaching, I'd actually scratch out the things so we could see it. We have the numbers. 2, 3, 4, 5, 6, and 7 are assigned to the 6 faces of a cube. Now this is something that you have to really have a good grasp of the language for, because do we assign the numbers more than once? They're really trying to trick you here. How do we know they don't assign the numbers more than once? How many numbers are there? There's 6. Why didn't they do 1 to 6? Because that'd be too easy, right? They do 2 to 7, so you're confused. Everything about this question is trying to confuse you, like all math tests. So one of these will be 2, 3, 4, 5, 6, and 7. So we can have like 2, 3, let's say 3 is there, 4, 5, 6, and 7. Everyone gets a prize, okay? So everyone gets a prize. Now, the thing is, for each of these 8 vertices of the cube, a product, no problem, a product of each of the numbers is computed, where the 3 numbers are the numbers assigned to the 3 faces. Okay, so what does that mean? Well, here's a vertice, right? Now, I know I don't have 3-dimensional drawing techniques here on the whiteboard, but let's say this face is 7, this face is 2, okay, and this face is 5, okay? So we have 7, 2, and 5, okay. All right, now it says the product of 3 numbers is computed. So what is the product of 7, 2, and 5? That's correct. Perfect. So we have 70. Okay, so we understand now what the question's asking us, or what the description of the question is. Okay. What is the greatest possible value of the sum of these 8 products? So what they're asking us is, we have 8 vertices. We're going to put different things in a cube that will allow us to calculate the sum of 8 things. Then we're going to add those together. The 8 vertices, the 8 V's, are all going to get added together. And what is the greatest possible value that could be? Yes?
I think I got with because each number is being used 4 times, like it's being used in like
3 times. But yes. Keep going, you're on the right track.
And like, so we can just times like 8 cube plus 2 cube plus 3 cube plus 4 cube.
Okay, yes, yeah. Now, here's the thing of it. They're all being used 3 times. So what you did is one of the solutions. You've solved one of the solutions. So that's great. So not everyone's going to get that right away. So one way you could do it is you could do a cubed plus b cubed plus c cubed, right? If you assigned each of these numbers, right? So it would be 2 cubed plus 3 cubed, cubed, plus 4 cubed plus 5 cubed plus 6 cubed plus 7 cubed. But that's not going to give you the exact answer because there's a few things that you're missing. That's part of it. That's the beginning of a solution. Did you have any further? That's how far you got. Okay, great. So that's one thing to figure out. Okay, there's another way. There's 2 other ways to do it. Your solution, I'm going to explore it further, but what you're missing is you're missing a few components to your understanding of the question. So I want you to make sure that you understand that first. So we have these things. If you want to know the easiest way to do it, okay, here's the easiest way to do it. And this one you'll do first, and then you'll double check. So we want the greatest possible value of the sum of products. Okay. Because we want the greatest possible value of the sum of products, we need those to be as high as possible. Okay. So how might we assign these numbers so that they are the highest possible number? Let's look at assigning each of them. Let's do it through algebra first. Okay? Are we good for time? Okay. Let's do it with algebra first. So, because we don't know what they are, when we don't know for sure which ones to put there, we should do it algebraically. So we have our cube. Now, there are 6 faces to the cube, like we said. A, let's label them. A, B, C, D. This one below is E. And right in front, I'm just going to label here, is F. So we got 6 of these. We know that we're going to multiply them all together. So we will have something like A, B, C. But the question is, we actually have to take into account that we aren't actually going to multiply all of them together. Which ones will never get multiplied together? In a cube, it will be the top and the bottom, correct? Because if we're going from the corners, the top and the bottom won't be multiplied together. So what we'll have to do is we'll have to make sure that the top and the bottom are on different products. So what we'll do first is we'll name each of the sides of the cube. Like I said, A, B, C, D, E, and F. And we'll have to make note of which ones are opposite, because they will never multiply. So A is opposite to D, B is opposite to E, and C is opposite to F. So we keep track of the fact that in this cube, these won't be multiplied. Then we have to think about all the possibilities of the adjacent sides. Once we do that, we'll actually have something that looks like this, our 8 products. Okay. Do you think that you could get to this point if you spent a lot of time with the question? You should probably be able to get to this point, or at least you will be able to get to this point after you've done a number of questions like this and we've walked through how to use these examples. But say you're at this point. Many students will stop here, okay? Because they're like, well, I don't know any of the numbers. But you actually do. You actually know that you can continue to go further. And as you know with some math competitions, just keep doing whatever you can do, and something will come out. So as you do this, you realize, well, A is in all, well, in the first 3, you have B in all of them. You can factor out the B, okay? You can actually factor out the B from the first 4. And you can factor out the F from the last 4. So then you can take the B plus F. And then when you put them back together, I'm not going to do it right now because I don't want to spend so much time factoring, but you can take out the A and the D, and then you can take out the C and the E. Now, what does the B stand for? Is it a vertice here, or is it a face of the dice? Face of the die. Exactly. Now, the face of the die has to be assigned a number. Do you remember what the numbers are?
2, 3, 4, 5, 6, 7.
Exactly. So one face of the die is being added to another face of the die. And that's being multiplied by another face of the die being added to another face of the die, which is being multiplied by another face of the die being added to another face of the die. Can we use the numbers only once? Yes. So we know we want the greatest possible. If we're multiplying things with each other, numbers with each other, do we want the highest numbers multiplied to get the greatest value? Exactly, we do. So how do we combine those numbers from this point so we make sure we get the highest possible?
You can do like the smallest, the biggest, second smallest, second biggest.
Exactly, right? 2 and 7, 3 and 6, 4 and 5. And what's the number we get?
9.
Exactly. And so we have 9 times 9 times 9, which you will know is 729. when you know your cubes, right? And there you have your answer. Okay?
Do you
Yeah.
have to memorize all the cubes?
Well, you'll memorize the squares, so you'll know 9 times 9 is 81. And from there, times 9 again, you're fine, right? All the squares you should memorize. Like, you want that on your fingertips. A little bit challenging, but now that you see it, it's like, yeah, I could totally do that. Not a problem. Let's go back to the question real quick, just to show you one final thing. Okay, there's more to this question, and I don't know if you've looked at math questions, but what number can you automatically eliminate?
I will try because
Of the answers, which of the answers can you automatically eliminate?
probably say 625.
Exactly. No. Well, here. Okay. So I'll explain to you because I've worked with writing these questions too. At some point, this number is way too high. You'll never get there. So you can eliminate that one immediately. Like this is if you're out of time. You eliminate that. You know that's not it. You know they're probably trying to trick you with the square root with this because that is a number that you take the square root of. So they're probably trying to do that. This is way too low when you get to the factorization. There's no way to multiply these numbers and get something that's that low. So you're kind of like, okay, great, it's 16. It's one of these two. At least you got 50% chances. Now what you were doing, I'm just going to talk about it because I'm not going to explain it, but what you're doing is right. If you took 2 squared, or 2 cubed plus 3 cubed plus 4 cubed, right? But you have to factor in the fact that you're taking 3 of those and that you're adding them, so you'll have to eventually divide by 3 as well. So you'll get 27 cubed divided by 3, right? So you miss those things, which is fine. And then you'd end up with 729. But like I said, with some students, they see this question and automatically they go, okay, it's simple, 7 and 2, this and this and this and this. And then I say to those students, no, you're right, it's good, congratulations, but if the question was 1% more complicated, then you would need the algebra for sure, right? So you should know how to do the algebra. So like I said, you get to the point where, okay, I can figure out the answer immediately with knowing that that's going to be 7 and 2, 6 and 3, 4 and 5, basically, and then I'll do the whole algebra to check it. And that's the same thing with your part C. There's 4 solutions, about 4 solutions to every question, and so one is a really quick one, but you have to really have a great grasp of all your math. So that's my second question. While we move forward, I'm going to leave the third question on, and if you're bored, you can look at it. It's very simple. You can solve it in 10 seconds. But other than that, we'll take questions. I know it kind of feels a little rushed, and I put you on the spot because it's like I didn't show up to take a math competition, and these are kind of challenging and whatever. Usually in the class, we're a little bit more, like a little bit more relaxed. But since we don't want to waste any time, we are always learning stuff. So, yeah. Did you have any questions at all? I've asked you so many.